Hey, welcome everyone to the first afternoon session. We have 5 talks in this session. The first talk is on approximating geometric knapsack via packings, and Arindam is going to give the talk.
Thank you. My name is Arindam Khan, and this talk is on approximating geometric knapsack via L packings. And it's a joint work with Waldo Galvez, Fabrizio Grandoni, Salvatore Ingala in ITSIA, Sandy Hedrich in MPI, and Andreas Wiese in University of Chile. Okay, so let's start with the definition of the problem. In geometric knapsack, you are given a bunch of rectangles, n rectangles, and each rectangle Ri has integral width Wi, an integral height Hi, and an associated profit Pi. We are also given a square k cross k knapsack. For example, in this instance, we are given 6 rectangles with sizes and profits, and we are also given a knapsack, square knapsack. And the goal is to find an axis parallel non-overlapping packing of a subset of input rectangles into the knapsack that maximizes the total profit. And there are 2 variants. In the first variant, no rotations are allowed. So think of add placement kind of problems where orientation is important. And in the second variant, you are allowed to rotate the rectangles by 90 degrees so that they are still axis parallel. And this problem is a generalization of classical knapsack problem and has a lot of applications in cutting stock, logistic and scheduling, ad placement, and so on. And there are 2 books on knapsack problems which list many more applications. And geometric knapsack is also a central problem in geometric packing and covering problems. There are several important problems related to this problem, such as independent set of rectangles, where positions of rectangles are fixed, and the goal is to find a maximum profit subset of rectangles which are non-overlapping. Then there is unspreadable flow or storage allocation problem, where horizontal positions of the rectangles are fixed. You can move them vertically, and the goal is to find maximum profit subset that satisfies the capacity constraints. Then there is 2-dimensional bin packing, where the goal is to pack all items into minimum number of squares. 2-dimensional strip packing, where we need to pack all items into minimum height fixed width strip. In fact, the best known approximation algorithms for 2-dimensional bin packing and strip packing uses a variant of geometric knapsack as a solution. Now, geometric knapsack problem is strongly NP-hard, even when all items are squares with profit 1. So we don't expect an exact algorithm in pseudo-polynomial time, even in pseudo-polynomial time. And we'll consider approximation algorithm. And this is a maximization problem. An algorithm is alpha approximation if for all input instances optimal is within alpha factor of the algorithmic solution. For this problem, the best known approximation is 2 plus epsilon by a result by Janssen and Chang from SORA 2004. And it works for both the cases with and without rotations. And even in the cardinality case, where all profits are 1, so you just want to maximize number of rectangles packed, this is the best known. 1 plus epsilon approximation is known for several special cases. For example, when profit of an item is equal to its area, or items are relatively small, or they are squares, so on. And this problem is also studied under the resource augmentation framework, where you can increase the knapsack size slightly from k to 1 plus epsilon k, either in both dimensions or even in one dimension. Then you can obtain almost optimal profit in polynomial time. There is also a quasi-polynomial time approximation scheme, which shows you can get almost optimal profit in quasi-polynomial time, assuming the knapsack size is bounded in quasi-polynomial in the input. However, in general, 2 plus epsilon is still the best known even in quasi-polynomial time. In our result, we break this barrier of 2 after 1.5 decades. And we show in the general case, without rotations, we can obtain 1.89 approximation. and with rotation 1.5 approximation. In the cardinality case, we can improve further without rotation 1.72 approximation and with rotations 4/3 approximation. In this talk, I will present a simpler 1.78 approximation for the cardinality case where all profits are 1 and rotations are not allowed. So let's start with the previous approaches called container-based packing. Now containers are axis-aligned rectangular region such that either it contains one large item, like the green box here, or the items which are packed inside are a horizontal stack, the blue square, or vertical stack, like the purple square, or all items inside it are very small in both dimensions, like the yellow box. Now, the containers are kind of one-dimensional knapsack instances, so they are kind of easy to pack if you know which items are packed in which container. And we call a packing to be container-based packing if all items are packed in some container. So in the previous approaches, we start with an optimal packing or any feasible packing and show that we can remove some items and still we can preserve alpha fraction of the profit such that every item is packed in a container and the number of containers is constant. And if this happens, then we can guess the sizes of the containers as well as the positions in polynomial time. And then we can use a dynamic program-based speeders for multiple knapsack problem to pack items inside containers. But there is a bottleneck of 2 in this approach. So consider the case when all items are long. So they have either width more than k by 2, half of the knapsack size, or height more than k by 2. Then you can trivially obtain a 2 approximation by just taking either the vertical stack or horizontal stack and apply one-dimensional betas. But the problem is this vertical and horizontal items, they can interact in a very complicated way. And it's not clear how to be factored 2 even in the cardinality case using container-based packing. So for example, if you pack these tall vertical items in a container, then you will not be able to pack the wide horizontal items in the bottom. So to handle this complex interaction, we go beyond containers. So first we define this L packing problem, which says you are given long items which have either height more than k by 2 or width more than k by 2, and you are also given an L-shaped region. And the goal is to pack a maximum profit subset of items inside this L region. Remember the previous base was 2 plus x7 for the problem. And first we give a p-task for this L packing problem. In fact, it's not very hard to see a pseudo polynomial time algorithm for L packing. So consider an instance of L packing and some optimal packing. Now one can assume that all horizontal items in this are placed according to non-increasing width, and they are also touching the right boundary. And similarly, for the vertical items, we can assume they are placed according to non-increasing height, and they are touching the top boundary. So like this. And if this happens, then we can find either a vertical cut which separates the tallest item from a smaller L region, or we can find a horizontal cut which will separate the widest item from a smaller L region. So we can easily get a smaller subproblem, and as these cuts can vary, can take order k possible positions, using dynamic program you can get the optimal solution in polynomial in k and n time. So this gives a pseudo polynomial time algorithm. So to get polynomial time algorithm, we prove the structural lemma, which is kind of one of the main technical contribution of the paper, where we modify this packing. So let's say we take the horizontal stack of items, we remove a small subset of items, such total profit is less than epsilon times profit of the optimal solution. and then the remaining items will either keep in the same position or will shift it down. So that will not create any conflict. And then the top coordinates of the horizontal items, it will only take polynomial number of values. So instead of k possible values, it will only take polynomial number of values. And similarly, we will do the same for the vertical items. And now the dynamic program, instead of polynomial in k, requires only polynomial in n number of values. So this gives a p-task for L packing. Now why this helps? So let's get to the 16 by 9 approximation for the cardinality case without rotations. So remember, we call long items which have longer side more than k by 2. So either the width is more than k by 2 or the height is more than k by 2. And we'll call short items which have both sides less than k by 2. Now if we take some optimal solution, let's call opt long to be the profit coming from the long items in the optimal solution, and opt short to be the profit of the short items in the optimal solution. So we'll give two packings. In the first packing, we'll only pack an L region using long items, and that will give 3/4 of opt long profit. And then we'll give a second packing which will pack using constant number of containers, and that gives packing at least half opt long plus 3/4 opt short. And if these two are true, then we can take the best packing, and that will give a 16 by 9 approximation. And remember, for first packing, we have a p-task for L packing. The second packing, if there are constant containers, we can find the best possible container-based packing. So these two together will give 16 by 9 approximation. So let's go for the first packing, or Algo-rindam, called L of the ring. So here we only consider the long items first, and as they are long items, we can create a stacks of rectangles by pushing them to the boundary, and that will create a ring. And then we'll remove the least profitable stack in the ring. So we still have 3/4 of the opt long profit, like this. And then we can rearrange the remaining items to get an L packing. And then we use our p-task for L packing, and we'll get 3/4 opt long profit. In the second packing, so observe that if opt is small, then we can just enumerate by brute force and solve the problem optimally. So we can consider opt to be large, and we define large items which have both sides more than epsilon k. So there are at most 1 by epsilon square such items, and as opt is large, they are only a small fraction of the opt. So if we just discard all large items, we lose a very small amount of profit. In this case, the dark gray rectangles are the large items. We discard them, and then all items have either height less than epsilon k or width less than epsilon k. And now we take a random vertical strip of width epsilon k with probability half, or a random horizontal strip of height epsilon k with probability half. Now what is the probability that a horizontal item is cut? So with half probability, we are taking a vertical strip, and it can be cut with probability 1. But if it's a horizontal strip and it's very thin, so it will be cut with a very small probability, or an epsilon. Total half plus epsilon probability. And for horizontal items which are short, it's even slightly smaller, 1/4 plus epsilon probability. So totally you will be left with half opt long plus 3/4 opt short. And once we remove these items, then we have some empty space, and we can push this to the boundary and use this extra space for resource augmentation. And then we can show there is a packing, container-based packing, which packs at least half opt long plus 3/4 opt short. So this works when there are no large items. If there are large items, it's much more complicated, and we have to take some other, use some other techniques to handle that case. The second case, when we have rotations allowed, then we use something called resource contraction lemma. So if a bunch of rectangles can be packed in a k cross k bin, then you can pack at least 2/3 of such rectangles in a slightly smaller bin. And then you can use resource augmentation to show existence of a container packing that gives 3/2 approximation. So resource augmentation is very well studied in geometric packing. We believe resource contraction will also be useful in this problem. Okay. So now the first open problem is finding a p-task even in the cardinality case, and also understanding the natural generalizations of L packing. For example, when we got the ring instance, we removed 1/4 of the profit. Can we get a p-task for that particular case? That will surely improve the factor. Or can we show a p-task for L packing with rotations? So with rotation, there is a problem. We don't know whether an item is rotated or not. So in case of L packing, that makes a slightly complex problem. And then as we solved only one L packing, if we have constant instances of L packing, can we get a p-task? That might give us some insight for the p-task for the general case. If you are interested more about this kind of problems and literature, you'll refer to the recent survey on this approximation and online algorithms for multidimensional ring packing. Thank you.
Any questions? So I had one question. What if you go to the next dimensions, three-dimensional?
Yeah, so it's more complicated. The best known, I think, is factor 6, but there, yeah, it's much more complicated.
There no hope of getting, is there a hardness?
No, so that's interesting. So this problem is not even known to be a px hard. So there could be a p-task. There is a result that is W1 hard, so there is no EP task for the problem. But yeah, there is a quasi-polynomial algorithm under some assumptions. So people believe we should have a p-task for the problem. But yeah, there is no known hardness result.
Any other questions? Okay, let's end this video here.